All right, so the same way we created those glycosidic bonds with the methoxy group, we can use amines as well. So for example, if you had glucose, and you added some acid catalyst and some kind of primary amine, right? We would have the same thing. This alcohol would get protonated. It would leave, forming a resonance stabilized carbocation intermediate. And then this guy would attack that carbocation intermediate. And that's the only position it's going to attack because that's the only position that creates that good leaving group. And so we can then attach amine nucleophiles instead. Of course, you'll get both anomers. So I drew the beta, but obviously you get the alpha as well. Let's take a look at why that's useful. And we're going to take a look at riboses. So in this case, we're only going to have 5-membered sugars. So there's one of our riboses, and then I'm going to draw another form of a ribose. So this one right here is just D-ribose. And then this one right here, note that it's missing that oxygen or that alcohol group right there. So this is 2-deoxyribose, right? And if you're thinking, that might sound a little bit familiar, right? These are the sugars that are found in your in RNA and then in your DNA, right? So these glycosidic bonds are also useful because they are found in our DNA, right? So there's your nucleosides right there. You can tell they're made out of a sugar, and then we'll let you learn on about these aromatic nitrogen combining rings. Again, with the RNA, we have this OH here. With the DNA, it's the deoxy. So we do not have that OH there. And then of course, one of the DNA bases is different, right? This one does not have a methyl group. This one does have a methyl group. Again, biochemistry, such a huge topic. If it's interesting to you, feel free to kind of pick what section is super interesting and go on with that section.